Good afternoon. I am Krishna Kumar from Krishna's classroom. Let us discuss two fascinating examples in the context of Riemann integration. Now, one of them is a function which is discontinuous at a countably many points on an interval AB, which is also dense on that interval, and at the same time the function is bounded and the function is Riemann integral. Now this is an example to Riemann himself, and it is nice to see such examples because they are the building blocks of analysis as this. So let me start with example. So the example one is due to Riemann. It's the features are, it's a bounded function to discontinuous at countably many densely distributed points on any interval AB three is Riemann. That is the sort of function that we want to construct. It's a fascinating construction. Nice to know how these things are constructed. And let us, this function is called Rx. Denoted by Rx. Now let us look at the construction. So let f be defined from minus half to half to R, defined by fx equal to x if minus half and equal to 0 if x equal to half or then is extended to R by periodicity namely by defining fx equal to f of x plus 1. So that's a definition. Now let us have a look at this function. The graph of this. Let us understand this. Zero, we have half minus half. 1 minus 1, 3 by 2 minus 3. We define the function in the following. The graph of the function will be this is the graph of the function, and at these points is divided into 0. Now it is further extended as follows. We extend it the following way. And similarly, on this side, you have the function extended. Now this is the graph. Right here, so this. So this is the function that you have defined, and likewise you have extended beyond this. Okay. So we will keep it as it is. That's a graph of the function. It's interesting to see that already you have discontinuities at minus half, half, 3 by 2, minus 3 by 2, then it goes on to 5 by 2 and so on. Okay. So f is now defined at all points it is periodic. Period 1. And it is just discontinuities, finite discontinuities. Minus 3 by 2. That is the general point that you get to be. Okay, so this is the nature of the function that we have defined. Now it is from this function that we construct R. So we have not gone ahead to construct the function R yet. So now we define R of x So that is the definition of Rx. Rx is equal to summation n equal to 1 to infinity f of nx divided by n square, x belongs to R. Is this well defined? I mean, that's the first question that you ask. This is well, we first observe that this is well defined at every point on R. Then we explore what are the discontinuities of this function. Okay. Then we observe that modulus of Rx is less than or equal to half of, and you see that f of nx is bounded by half. So that's how you get this sigma t square. So this is finite. Therefore, the function Rx is uniformly convergent. The series is convergent. That's the first observation that we make. Now let us explore what are the points of discontinuity of R. So for that, I think this is purely something I can just state and go ahead with it, because you are supposed to explore all these things. But just show you how I have been exploring this, and maybe a lesson or two that you may learn from it may help you in many circumstances, where I believe that while learning mathematics one should explore examples thoroughly, and that's one reason. So the first thing that you observe is this: what this function is. Now it is quite nice that it has been well defined. And let us see how this function looks like. Maybe you may not be able to look at it, but you can explore the individual terms of this. So what are the individual terms of this? Okay, let us take for. So let us explore the terms of the series. See that the case for n equal to 1 For n equal to 1, okay, so let me just write down the C's. So Rx is equal to, what is the first term? The first term is going to be fx by 1 plus then f 2x by 2 square this is what the series is called. Now the first term we already have. This is f. This is y equal to f of. Let us look at the second term and possibly make some inferences about the third term, and that's very easy to do. And maybe now after that you can understand everything. So let us explore. What is this f of 2x by 2 square? Now this is the term that we are trying to explore. Now you see that f of 2x, this is 1 by 4, is equal to 2x for this is what the definition is and extended. So let us see what are the, so the function, the graph of the function, let me try to picture this. Maybe worthwhile doing because you would get a feel for the function, and getting a feel for the function is always helpful in getting some insight into what goes on. So let us look at the graph of this function. Now this is equal to fx equal to 2x, so f of 2x equal to 2x. And what is this interval? This interval is minus 1 by 4 less than x less than. Therefore, once again you see that the function is like this. So this is minus, this is 1 by 4. This is minus 1 by 4. And then you have 0 here, and half here, 3/4 here, 1 here. Similarly, minus half, minus 3/4, minus. Now, what is the maximum value that the function takes? The maximum value that the function takes is possibly at the extreme n points, which it doesn't happen because it's an open interval. Therefore, it is bounded between minus half and plus half. So we take 1 by 4, 1 by 2 here, minus 2 by 4, minus. So the first block in which the function is defined is between minus 1 by 4 and plus 1 by 4. And there you see that the function takes changes between them. So you get essentially something else. And then of course the function is further defined like this. By extending you will get this one. Similarly, you have the minus there, it's 3/4 by that time, and so on. Okay, and then of course what you have is that it will be something like this. Something like this. We have to. And similarly, here we are going up to this is a sort of the graph of the function f of 2x. But the second term is essentially f of 2x by 2x squared. So what you have to do? You have to scale it down by a factor of 1 by 4. So if you scale this down, it will go up to 1 by 8. Okay, so the function will be bound with this. Something like this. So this is going to be so everywhere the function is like this, and over this part, over this part, it is going to be something else. And then you have something like this. Now this is the scale one. Scale one that you have. And this is again the same. You are dividing it by. So the second one that I have drawn is, so this is 1 by 8. And this is minus. Okay, so it is going to be switched between these. So we get an idea where the discontinuities are. So the first term has discontinuities. So f(x) what are the points where it is discontinuities? This discontinuities at minus 3 by 2, minus 1 by 2, 1 by 2, 3 by 2. Now what are the points of discontinuity for f? So this can be written as the set of points 2l plus 1 under. Okay. These are the points where we have discontinuities. Now f2x is this rightly from L belonging to Z. So you get all account for all things. f2x discontinuous. See, 2x equal to 2l plus 1 by 1 times half. Therefore, at x equal to now this is essentially, if you try to plot this, actually write down this is going to be for L equal to 0, it is going to be 1 by 4. Then 5 by 4. Minus 1 by 4. Minus 3 by 4. These are the points where there is continuous. Therefore, in general, the function has discontinuities at points so f nx here. Then what is that you require? Nx has discontinuities in something like m n by these points where is a odd multiple of okay. Therefore, each term has certain discontinuities. So you see that the discontinuities of R is actually spreading all around. Okay, and it spreads to a dense subset of. Therefore, one can see that Rx has discontinuities at countably many points which is essentially the discontinuities of all these points. Okay, right? And at every one of these points, it has a jump discontinuity, which is the union of all discontinuities of fnx for what we want to study is the magnitude of the discontinuity. What is the magnitude of this discontinuity? Okay. So in short, R has discontinuities at x if and only R has discontinuities at x if and only if x is equal to okay, where the common multiple of or the common divisor of m and 2k equal to 1. That means they are basically trying to each other. So this is the condition. And then out and you can list them out and then try to find them. Okay. Therefore, now let us try to find out what is the nature of this discontinuity or how much the function jumps at various discontinuities. Okay. So we observe the following. Now you see that if you look at what happens, what are the values of the function at the points of discontinuity? The values of the function at the points of discontinuity are 0. Okay? Right? And from the right it takes a certain value and from the left it takes a certain value. Therefore, there is a jump discontinuity at any point of discontinuity. And it is contributed by various terms of the series, as you can see. Now that I hope you will analyze term by term and first 3 terms or 4 terms you take and you get it. It's a nice pastime but quite interesting to understand this. Now we see that if you take any point of continuity at any point of continuity, we have R minus. It's continuous from the right and continuous. If one of them fails to hold, then it becomes discontinuous. But we know that all the points of discontinuity, it is discontinuous from the right as well as from the left. At any point of discontinuity, Rx R not equal to Rx not equal to minus. In fact, at the points of discontinuity, this is equal to 0. Okay. Therefore, at the points of discontinuity, we will evaluate this. What are the points of discontinuity? It is the points of the type x equal to m by 2. Therefore, at any point of discontinuity, say this condition equals to 1. We will write down the jump, the discontinuity that you have. You have R x plus minus R x. Now R x plus is, from the left hand side, it has a negative value. Rx plus has a negative value, whereas Rx is 0. Therefore, this is equal to, you can compute this, this is equal to minus 1 upon 2k square. Little bit of work is required. L equal to 1 to infinity 1 upon whole square. And this sum is essentially equal to minus so here you are using the relation sigma L equal to 1 to infinity 1 upon this. So what you have is, see, for instance, at the point see, what is the function? The function is like this, and from here onwards the function is like this. So what happens? This is R plus term will have a contribution from here. R minus will have a contribution from here. Okay, in fact, there will be at this point of many of the terms may have discontinuities. So they all add up. That's what you have to find out. Which terms will contribute to the jump discontinuity at this point. And that you will get if you write down the series properly. Similarly, Rx minus is positive. Okay? At the point of discontinuity. Therefore, this is equal to 1 upon 2k square which is equal to this. I think you need a little bit of work here. Pi square line. So we have estimated the discontinuities at the magnitude of the discontinuities at the points of discontinuity. So we have found out what are the points of discontinuity. First of all, and at those points we have actually computed the quantum of discontinuity. Okay, so here x is taken to be, see here x is taken to be m by 2k, where now this you can actually work out what are the points, because once half minus half 3 by 2. See, 1 is not a point of discontinuity. So 0 is not a point of discontinuity. 1 is not a point of discontinuity, and so on, where see at all those points the function takes a value 0. Okay. Similarly, when it comes to the next function, that is f2x, you see that the points of discontinuity are minus quarter, then it is not, half is not a point of discontinuity for that. It's 3/4 and so on. So you can write down that essentially it will turn out to be this set of points, and where you have actually you can estimate the discontinuities. That needs some little bit of trying your hand. That is a little bit of time on, but explore it, and that's a good exercise to prove that these two are the quantum of discontinuities. Now we make the following observation. The points of discontinuity of R form this, I think, needs some. We have to use little bit of analysis to show that these set of points are dense, because you know that at every stage more and more points are coming into the becoming points of discontinuity, because each term of the series contributes infinitely many points of discontinuity. This is what, but still it's comfortable. Now we claim, the next claim is, this is the R integral on many compact interval of any compact interval this is the next thing that we want to observe. So for that we recall, we have the following here. So we recall what is that? Let us say that. Let f from AB to R be a bounded function such that the set of points D epsilon, D we denoted, the set of discontinuities D we denoted by this is the magnitude of discontinuity that we have f at the point x is at all points of continuity omega fx is equal to 0. This has to be A null set. Now this amounts to proving that then f is we look at the following set D epsilon. D epsilon is the set of all. So consider D epsilon for some epsilon positive. For epsilon positive, but epsilon now you see that what is this set in the present case D epsilon is equal to the set of all x belonging to A2 such that where x is equal to m by 2k. These are the points of discontinuity with common divisor of m and 2k equal to 1, and what is the discontinuity at these points? At each point, you see at m and 2k, we have already computed the discontinuity. The discontinuity is that this is actually pi square by 16k square, and the difference between r plus rx plus minus rx minus is going to be twice this. Therefore, this is the discontinuity that you have is the magnitude of the discontinuity at a point of discontinuity is 8k square, and this is greater than, these are the set of things. Okay, now we have to understand this set. Now my claim is that we claim that this is a finite set. Okay, make the following observation. What is your Rx? Rx, you look at it, is going to be fx plus f qx by u square plus f 3x by 3 square, etc. So the general term is f of, the general term is that each one of them has infinitely many points of discontinuity. But suppose you take confine yourself to the interval AB. Suppose x belongs to AB, which is a common. Then you see that each term has only finitely many discontinuities in this interval. Okay. Then that is the first observation that we make. The third thing is that suppose one by n square is less than then you see that if you insist on the discontinuities to be greater than the jump discontinuity to be greater than epsilon, then what happens? Okay. You see that for terms f of the terms f of nx for n greater than n has of magnitude less than okay. Therefore, all those terms do not, come into the reckoning. So what we have is the terms involved are the terms for which the discontinuity f and the terms in the series involved are, so it is going to be something like this. So there are only finitely many terms of Rx contributing to the discontinuities of magnitude greater than epsilon. Okay, because only finite, see, each term has finitely many discontinuities, and only finitely many terms of the series matters, because the tail of the series has discontinuities where the jump discontinuity is less than. So there are only finitely many terms of Rx contributing to the discontinuity of I input. So how many? Therefore, hence the class of discontinuities of R finite set. And hence it is a null set. I mean, you recall the definition of null set. That means you can say that d epsilon for the function R true. This essentially implies that I can write Riemann on the interval on any compact interval and that is one of the theorems, and the set of discontinuities of R form a null set provided d epsilon is form a null set. We are making use of that result. So you get the and hence the Riemann integral. I believe this is a fascinating example and has played a crucial role in the development of analysis. It is due. I think I will stop here. Thank you very much.